We have discussed in the previous video that conservative forces are forces in which their work done is independent of the path. So the work done by these conservative forces depends on the initial and final position only. It doesn't depend on the path we take to go from an initial position to the final position. We say it's independent of the path. So conservative forces that we usually encounter are the gravitational force, or we call it as weight as well. Second one is restoring force due to spring. And the third one is Coulomb and electric force. So these are the conservative force that we usually encounter. But for the third one, Coulomb force and electric force is something that you learn in semester 2 when you come across the topic of electrostatics. So we will not discuss that in this chapter, so we will not encounter Coulomb and electric force in chapter 5. So you need to know that conservative force in chapter 5 that we are learning right now is either due to gravitational force or it's restoring force due to spring. So in this video, we are going to try and prove that gravitational force is a conservative force. How are we going to prove it? We set up a situation with an initial and final position. Then we try to determine the work done by this gravitational force to go from initial to the final position using different paths. So we set path 1 and we find the work done by gravitational force to go from initial position to final position using path 1. Then we will find also the work done by the gravitational force to go from an initial position to the final position using path 2. So if the two paths generate the same amount of work done, then we can infer that this work done here is independent of the path. No matter what path we choose to go from initial position to final position, we will still get the same amount of work done. If that's the case, we are directly proof that this gravitational force is indeed a conservative force. So let's try and do this thing right now. So let's say we have an initial position and a final position, and now we'll create two different paths to go from the initial position to the final position. You can imagine this final position is somewhere higher above the ground compared to the initial position, and it's somewhere on the right of the initial position. So somewhere on the right, higher ground. So path 1 will be to go straight in a diagonal fashion, straight away go from the initial position to the final position, the most direct way of going from initial to final. So this one, let's say the distance traveled is 10 meter and the angle is 30 degree above the horizontal. So we call this path 1. And we also have a path 2, which is sort of like a zigzaggy pattern in which you move horizontally, then vertically, then horizontally, then vertically until you reach the final position. So the length for each section of the distance are clearly indicated here. So we have path 1 here and we have path 2 here. We will try to determine the work done by gravitational force when it moves using path 1. Then we will find the work done by gravitational force when it moves through path 2. Then we'll see whether the two generates the same amount of work done. So our gravitational force is our focus right now. So let's try to determine the work done if we use path 1. So for path 1, we know our force, our weight is always pointing downwards. How about the displacement? So we know that work done is always force and displacement and the angle between force and displacement, right? So our displacement will be indicated as this black arrow over here. So this is weight, this is displacement, and angle in between them will be 30 plus 90 degree, which is 120 degree. So if we do our substitution, we have the magnitude of weight, the magnitude of the displacement, and cosine theta, where theta is the angle between the weight and the displacement. So if we perform our substitution for theta, we know that theta is 120 degree because it's 30 plus 90. So according to trigonometry, cos 120 degree can also be written in another way in terms of the basic angle, which you might have learned before in maths. So you can re-express it as negative cos 60 degree. This is trigonometry, okay? So negative cos 60, if you interpret it this way right now, you can rearrange negative, bring it outside, then you can get S1 cos 60 degree instead. So S1 cos 60 degree, it's just resolving this vector S over here to the component, to find a component that is parallel to the weight over here. cos 60 is just resolving this vector s here to find the component that is parallel to the weight. But now we have this negative sign here because this s1 cos 60 degree here is pointing in the opposite direction to the weights that we have over here. That's why we have the negative sign. So after that, what do we do is just rearrange our equation. Well, this is the s1 cos 60 degree that I mentioned earlier. And if you do your substitution, mass 5 kg, your acceleration due to gravity 9.81, your distance, your displacement magnitude is 10 meter, and cos 60 degree, you should be able to get the answer of negative 245 joule. So this is us determining the work done by gravitational force if the block here uses path 1 to go from the initial position to the final position. Now let's move on to path 2. For path 2, we'll be taking this zigzaggy pattern to go from the initial position to the final position. So if we are finding the work done using path 2, we'll have to split our work done into 4 different sections and add them up. So this first term here represents the work done when this object moves from the initial position to this point over here. The second section will be the work done by gravity when the block moves from here to here. The third term will be the work done by gravity when it moves from here to here. When the fourth term here will be the work done by gravity when the block moves from here to here. So if we sum them up, there will be equals to the work done for this block to travel from the initial position to the final position using path 2. So if we compare that, what we are going to do now is we are going to substitute in the angle only. Similar to what we do here, we substitute in the angle. So for here, you can see that the weight and the first portion of the displacement, which we call it as displacement 2A, path 2 section A, the displacement and the weight is 90 degree, has an angle of 90 degree in between them. So you can see I substitute 90 degree for theta 2A. For theta 2B, which is the angle between the weight and this displacement pointing upwards, you can see that they are in opposite direction. Therefore, theta 2B will be 180 degree. For the third section of the displacement, you can see that the displacement is pointing to the right, whereas the weight is pointing downwards. So the angle between these two vectors will be 90 degree, and here we substitute in 90 degree. For the fourth section, you can see that the object is moving upwards, the displacement is pointing upwards, whereas the weight is pointing downwards. Again, opposite direction, 180 degree. So once we have substituted in our angle, what we do is we know that according to trigonometry, cos 90 degree will be equals to 0, whereas cos 180 degree will be equals to negative 1. Now, if we have 0 over here, that means these two terms here will disappear. Then we are left with these two terms only. And since this is a negative sign, we bring in front the negative sign, and we do a bit of factorization, factorize out the mg, then you should arrive at an equation that looks something like this. Now, at this point, you should notice something interesting, because S2b and S2d is the displacement of this portion of the journey and this portion of the journey. So if you add up these two vertical displacement here, essentially what you're doing is you're finding the change in height of the object when it moves from the initial position to the final position. And this is exactly the same as what you have calculated here for S1 cos 60 degree. So I believe you can see there's a similarity between the structure here. It's negative ng in front, negative mg in front. But for here is S1 cos 60 degree, which is the same as the S2b plus S2d that we have over here. So you can see that the equation are structured the same and the content that it has inside are identical actually. So you should know that if you calculate everything, you can take 2 plus 3 over here, then here inside will be 5, multiplied by 5 kg, multiplied by 9.81. You should be able to get the same exact answer, negative 245 joule. So now we can observe that by using path 1 and path 2, our work done by gravity will be the same answer. Both of them are negative 245 joule. So in that case, we are actually proving that work done by gravity is the same for both paths. Therefore, gravitational force is a conservative force. Because no matter I choose path 1 to go from initial position to final position, or I choose path 2 to go from initial to final position, I will still get the same amount of work done. And the work done is essentially determined by the mass, the acceleration due to gravity, and the change in height that we experience over here. So S1 cos 60 degree and S2b plus S2d here are essentially just the change in height. So we can re-express the equation that we have here in terms of negative mg change of height, and this one will be negative mg change of height. Well, I'm actually hinting something important because mgh is similar to, yeah, gravitational potential energy. So later I will show you why conservative force is important, because we are going to relate it to the idea of potential energy. So this is an example of a conservative force, and in the next video we will show an example of a non-conservative force by proving that the work done will be dependent of the path for non-conservative force.